Okay, this lecture is going to leverage what we already know about Newton's law of gravitation, but I really want to spend this time focusing on why your textbook or other people call this Newton's universal law of gravitation. There's a big difference there besides just calling it the law of gravitation versus universal gravitation. And one of the things that we commented on about Newton in class is that, you know, in his book, The Principia, he has this quote that says, "If I have seen further, it is because I have stood on the shoulders of giants." And we mentioned many of the giants in philosophy and human thought and physics in this class. But I just want to point out a few of them that maybe we had overlooked. Obviously, there's some that go all the way back to people like Pythagoras, but there are some on this list here that existed around the same time as Pythagoras as well. Some of the giants are Eratosthenes, who was one of the first people to measure the radius of the Earth. This is a name that's familiar from class because if you remember our second laboratory together, we used the Eratosthenes method to measure the radius of the Earth. And you can do this, as we've seen, with some amazing accuracy, and this was known from a very long time ago. Hipparchus was able to estimate the Earth-Moon distance. Huygens was most known for optics, measured the Earth-Sun distance. Copernicus gave us the sun at the center of the solar system. A guy by the name of Tycho Brahe just took gobs and gobs of data, of astronomical data, that became so useful in so many aspects of looking at the heavenly bodies. But one of the people who really put it to use was a name that I'm sure we're all familiar with, Johannes Kepler. And from those, of course, and making his own observations, he was able to deduce what he called the three laws of planetary motion. Now, I bring this up because this is going to be the link that takes us from Newton's law of gravity to calling it a universal law of gravitation. Okay? So let's see how that goes. But before we do, let's just remind ourselves, what is Newton's law of gravity? It's his capital G, M1, M2 over R squared. And I refer you to the lecture on gravitation, where we talk about how he came up with all these numbers, especially mostly the Newton's universal constant G. And I refer you back to that lecture for the value of it. Okay. This is very important because what we're going to be basically shooting for here is really Kepler's third law, okay? And Kepler's third law is an interesting one. So if we come over here, using the terminology of law for Kepler's third law is a little bit loose because when we think of laws in physics nowadays, we really think of something that is very rigorous mathematically or speaks the language of mathematics. The way that we want to think of Kepler's third law was that he was able to make an amazing empirical observation. Namely, he was able to use observations and data to come up with something absolutely amazing. That if you have a body in circular motion, his law actually extends to elliptical motion as well. But for the moment, we're going to just focus on circular motion. That if you have a body going in circular motion around another body, and we typically call this M1 and M2 if we're talking about a Newtonian system, we know that there is a distance between the two of them that we can always define, and we've been calling this R. And we know that as the body M2 goes around M1, it will eventually go all the way around and complete a circle, and we have circular motion. And associated with that, we know that we can define the period, namely the time it takes for this motion to complete. Kepler was able to observe by using his own and Tycho Brahe's data that for each of the objects in the night sky in the Copernican system, namely when we take, for example, the sun being the thing at the center and one of the planets going around it, he was able to observe that if you took the period of each of those and squared it, for each of the objects he could observe, this was directly proportional to the distance, the estimated distance between the objects cubed. Now, I think we need to appreciate how amazing this is. This was before the time of Mathematica or MATLAB or any computational program to help him look for this sort of relationship, and it's comparing a square to a cube. Now, one can say that, well, it's also amazing that he was able to do this because, we had were effectively cruder telescopes back then and only optical telescopes. But he was able to make this observation for the planets as well as for the moon going round the Earth. And we know that where we got some of these values from our previous discussion. So how can we use this to convince ourselves that Newton's law of gravity is truly universal? Well, using the people that we called giants before, okay, let's take a system that we know some of these values for. In fact, we could even take it one step further. We don't need to make reference to any system that we know the values, because what we would like to see is, can Newton's law of gravity, this one right here, predict something that looks like Keplers' third law? Well, let's see if we can use what we know from our discussion of basic gravity and the material from chapter 9 to put all these pieces of the puzzle together. So all we need to do is assume that we have something going in circular motion. If we make the assumption that it is going in circular motion, then we know that Newton's law of gravitation says that the force of attraction between the two will be given by this equation right here. But if it's going in circular motion, we know then that this is the same as saying that we are in a centripetally accelerating, or a system with centripetal force acting on it. So right away, we can cancel out the mass of the object in motion, which tells us that, namely, the planet that we're talking about, or the satellite, if you will, that we're talking about, makes no difference in this problem. For that matter, we can even go a step further and cancel one of the radii. So let's just do that and see that our equation already simplifies now to gm1 over r is equal to v squared. Mind you, that equation should not be surprising, because that equation is also identical to one that we can get from using nothing more than conservation of energy. Now, just to keep this as general as possible, I'm going to get rid of the reference to M1, okay, and instead I'm going to call it M sub c for the object at the center of the circular motion, which for this case could be the sun, or if we're talking about the Earth-Moon system, this would be the Earth. But basically, it's the object at the center, and r, as always, is the distance from center to center. Now, let's use some of the subsequent equations from our previous chapters. Since this is going in circular motion, then we know that we can relate v to the angular velocity, which is equal to omega r, which therefore, since in the equation below we're going to need the square of it, which gives us omega squared r squared, because whenever we square both sides, we have to distribute everything throughout. Okay, well, that's semi-useful, but I mean, in reality, we can't really, at least back in Kepler's time or in Newton's time, he couldn't measure with a photo gate or something the rotational velocity. So let's see if there's some other mechanism that we can use. For the moment, let's just write the step that we're at, namely that this is going to be omega squared r squared. Okay? If we take this now and we simply cross multiply, then we see that we're going to have g, mass at the center, is equal to omega squared r cubed. And all of a sudden we're starting to see something interesting, that we now have an r cubed on the right-hand side. Now, using some other material that we learned from chapter 9 in the rotational motion chapters, we know that omega, the angular speed, another word for this is angular frequency. So we can relate this to the regular frequency, which is 2 pi times the frequency. And we know that frequency, how much something occurs, is related to the period by being 1 over the period. So this is really 2 pi divided by the period, which then allows us to make another equation that we're going to use to substitute, since we need the square, is that omega squared is 4 pi squared over the period squared. Upon plugging that red piece into this equation here, we then see that we have g, mass of the object at the center, is 4 pi squared r cubed, a whole thing divided by the period squared. And now if we cross multiply one more time, we get something truly amazing, which must have knocked Newton's socks off. Namely, that we get g times the mass of the object at the center times the period squared is equal to 4 pi squared r cubed. And namely, by starting from Newton's law of gravitation, he was able to now take Kepler's third law, namely that the period squared is proportional to r cubed, and take it from a proportion and make it an actual equation. By making this an actual equation, then we now know the constants of proportionality, and look at the constant of proportionality that's in there, namely, we got a 4, we got a pi, well, pi squared technically, and we got Newton's universal constant floating around in there, and the mass of the object at the center, which in the heliocentric system would be the sun. This must have been amazing day, happy face for Newton. How can we use it to know that it's true? Well, since Tycho Brahe was kind enough to give us a tremendous amount of data, and Kepler knew that period squared was proportional to the r cubed relationship, one can then take this and, using Newton's constant for g, using the mass of the sun, using 4 and using pi, could see if this relationship held for every object that they can observe with Brahe's data. And because it's Isaac Newton, we know the answer was it always held. This proof right here, namely of taking Newton's law of gravitation, and think about this, it's using numbers that were discovered here on the Earth. The capital G, if you remember our previous lecture, the capital G was defined here on the Earth. But we find that using those numbers and applying just the simple equations that we have from Chapter 9, we can resurrect and in fact strengthen Kepler's third law and take it from being a proportionality to an actual equation, put it to the test on the data, and wouldn't you know it, that number g holds for those other objects, namely the other planets and things like the moon. This is one of the first places where we see physics that we deduce here on the Earth showing itself out in the heavens. This is why it earns the name Newton's universal law of gravitation, and not just the law of gravitation. Believe it or not, that universal gravitational constant g doesn't just stop there. We know that eventually Newton was usurped by Einstein in having a more correct theory of gravity called general relativity, but Newton's gravitational constant, capital G, is still there even in Einstein's theory of general relativity. Now that we have this equation, and it is a real equation, not just a proportionality as in with Kepler, we can use this equation to figure out all sorts of interesting things about things like the planets, satellites, etc., and that will come in our next problem-solving session. Until then, I hope that this is some insight into the real power of taking physics that we can learn here and putting it to use in the universe around us. Much like Newton, ladies and gentlemen, until next time, never stop thinking.